Okay, we're going to talk about how to find directional derivatives. So you already know the partial derivatives of a function. So df dx and df dy, these are the partials. And you can think about it as how the function changes along these directions, the x direction and along the y direction. But it's obviously there are more directions than this, right? You could ask for how does f change along this direction? If this direction is given by some unit vector u, you might ask for what is the rate of change of f along u? That's the notation that's used, and this is called the directional derivative of f along u. And u, well, it's a unit vector. So for example, if you have I, so u equals I, then it's just di of f, that's just the rate of change in the x direction. So it's just partial derivative of x. If you use j, so the y unit vector, then dj is just the y partial derivative. And what else can u be? Well, it'll just be some vector in general, ux, uy, and its unit, which means it's just the square root is 1. Right? Because if we have I, then the length of I is the square root of 1 squared plus 0 squared. That's 1. And similarly with j, we should have the same thing. Okay, so how do you actually compute the directional derivative in these cases? Well, it's actually just equal to some combination of partial derivative in x and the partial derivative in y. So it has sort of, you can think of it as x parts and y parts. Just like a direction, u, has x parts and y parts. So it actually turns out you do the exact same weightings. So you do ux times fx plus uy times fy. So the direction size tells you how much of fx to include. And so there's a compact way to represent this. It's just the dot product of u with the derivative of f in vector form. So the vector derivative, this is called the gradient. And this thing is just fx, fy. Similarly to how we have ux and uy. Yeah, there's an x component and a y component. And it turns out you just stick the partial derivatives in here. And you can think of this as the 2D vector derivative. In 1D, we just have one component. So it's just we use a scalar. And that's just df dx. But in 2D, we have two derivatives, so we need a vector. Okay? So let's find an example of how do you actually compute this thing. So if f of x, y is the logarithm of x squared plus y squared, the problem will be to find the directional derivative at the point 1, 2, say, and in the direction of the vector v given by -2, 1. So if you like pictures, the vector v, it'll look something like this. it'll have a large x component and a small y component. That's why I drew it like this. Okay? And so I think you can break this down into several steps. The first step is you can compute the gradient of f. So fx, fy, that's what that means. So what you do then is you just compute each of these things. So I'll just do this on the side here. Fx, it's 1 over the thing inside the logarithm. Fx, remember I'm using shorthand notation. Fx is df dx. And so now it's times, if I'm taking the derivative in x, it's times the derivative of the thing inside the logarithm. So x squared plus y squared. Obviously the y does nothing. So it's 1 over x squared plus y squared times 2x. And if you want to do fy, it's 1 over x squared plus y squared, the thing inside the logarithm, times the y derivative of the thing inside the logarithm again. And you can see it's going to be something similar by symmetry. So we get our gradient, which is 2x over x squared plus y squared, and something very similar in the y component. So now we just evaluate it at our point, which is 1, 2. So we'll just plug 1, 2 in here. So it's 2 times 1 over 1 plus 4. Then we have 2 times 2 divided by 1 plus 4. So it looks to me like this is 2/5, 4/5. Okay, that's step 1. Because remember, we're using the formula du f is u dot grad f. So now we need u. Okay, so this is and remember this is the direction of v. So v divided by its length, this will give you the direction. Right, because the vector is magnitude times length. I'm sorry, it is a magnitude times direction. So all we need to do is just take v and divide it by the square root of the stuff that v has. So if you recall, v is 2, 1. So 2 squared plus 1 squared. You can stick a negative sign if you like. So this is v divided by square root of 5. And explicitly, of course, this is minus 2 over square root of 5. This is 1 over square root of 5. That's our u. So now our last step is just we need the dot product. And remember, this is just ux fx plus uy fy. So if we take u dot gradient f, we'll just have this dot product minus 2 over square root of 5, 1 over square root of 5 dotted with 2/5, 4/5. So then we just do component by component. And this is minus 4 over square root of 5 times 5 plus 4 times square root of 5 times 5. This is, of course, just 0. Which is as nice as you can hope for. Okay? So I think if you break it down into these 3 steps, directional derivatives should be straightforward. I think the hardest parts are probably just computing the partial derivatives, because calculus is always the hardest part. And the rest of this is just arithmetic. Okay, thanks for watching.